Hello students, so welcome to today's lecture. If you remember, we were still discussing absorption spectroscopy, and in that now from the experimental consideration of absorption spectroscopy, I move little bit in industrial application and how UV visible spectroscopy can be used for measuring and quantitating the biopharma products as well as in clinics how can be used. So, if we are using it for industrial application, stringency for experiment and instrument goes up. So, today I am going to give you some hint or some concept how we can do it or how we can use this spectroscopy in industrial setup, putting the all stringency in place and what we can do it. So, you remember the concept is very simple. Beer-Lambert law, A equal to ECL, it is a simple theory, but if you look at the real spectrometers, in this simple theory also there are three critical errors that can come and that can affect the protein quantitation, the biomarker detection and research validity, and therefore, even if it is simple, you have to be very careful because like if you are doing some biomarker detection, you cannot take a chance and report a wrong value, that lots of they are on the stake, and even the quality assurance or quality control of your product which is protein based drug, you cannot take a chance because that gives the information very wrong on your biopharma product. So, one has to be very critical of the data and vigilant of the data that is coming out even from this simple experiment of absorption spectroscopy. So, here are the critical instrument what are the critical instrument parameters that can induce some of the error. First is spectral bandwidth, right. It can lead to something called peak distortion. So, if you remember, there is a absorption maxima, that is lambda max. If there is a spectral bandwidth error, this can shift by 2 to 5%, it can shift that can induce 2 to 5% of error. Another can be wavelength accuracy. If your wavelength are not correct and calibrated, your E here absorptivity will change and that can lead to like a 0.04% in per 0.1 nanometer at lambda max error, right. The third thing, how well your instrument is built, stray light is coming or not. So, if stray light is coming, that can also change and it can be irreliable if your stray light is coming. So, it can change the absorption by 2.5 or something. So, for doing all those, now USP is United States Pharmacopoeia, has come up with some chapters and put up some standards. What will be the parameters for these? USP basically sets the standard and all the industry has to follow it. It is a very nice guideline that they put forward. So, wavelength accuracy should be plus minus 0.5 nanometer, the spectral bandwidth should be less than 2 nanometer and the stray light should be 0.05% of transmittance. That means linearity should be more than 0.99%. Right. So, this is the basic concepts. So, what we are going to learn today is how we are going to have a spectral master spectral bandwidth, wavelength calibration, stray light correction, and when you are getting your instrument, you need to do some qualification of the instrument. So, which is called IQ, OQ and PQ, installation qualification, operational qualification and performance qualification. So, in academic setup generally we do not care about these, but in industrial setup this is of paramount importance that each instrument that we obtain, it has to go through qualification of the instrument and that has to be done periodically, and that is these three things must be done. And then you apply the validation and troubleshooting strategy if something is wrong, calibration is not there or so, and how you can select the optimal setting for protein analysis and biomarker detection. So, let us start. What are the practical consideration and how we can overcome this real world instrumental error. So, instrumental error can come from these three that we discussed. So, you see our instrumental parameter that we are observing is absorption A equal to ECL. It appears simple, right, but as I said there are systematic error can be introduced because of these three parameter, and that can lead to protein quantification, biomarker detection and overall our research validity. So, see if there is a change in a spectral bandwidth, if your bandwidth is not correct, right. So, bandwidth means range of wavelength that is reaching to the sample nominal at lambda. So, if that is not happening, the peak distortion can be introduced, right. Peak distortion, peak is not very symmetrical because of the instrumental error, and then lambda max can shift, and that can lead to 0.5 to 5 nanometer error, and that can lead to protein quantification error by 2 to 5%. You see 2 to 5% is not small, it is a big number, I will show you why. Then wavelength accuracy, it's a like a how closely, so wavelength accuracy tells how close to actual wavelength that we have selected. If we have selected 280, it should be absolutely at 280, it should not be at 279 or 278 or 282 or something like that. So, less than 1 nanometer it should be, 0.1 to 1 nanometer it should be. If that happens, if the wavelength is not correct, it can change the extinction coefficient by say 0.4 to 1% at lambda max. And third one, stray light, if the stray light is coming, unwanted wavelength is reaching to detector. So, you see our detector is detecting whatever is coming out from your sample, not from the stray light. If that is coming, then it can lead to high absorbance error, right, in the transmittance, and that can lead to change in the measurement value by 2.5 or something like that. So, stray light absolutely should not come, and therefore, manufacturing this instrument should be done with a very care that no stray light should reach. Let us take an example, real world scenario. Troponin C, you remember what was that for cardiac biomarker, myocardial infarction, that is what troponin 1 measures, right. So, somebody has a issue with heart, finally doctor suggests first ECG is done, then say TMT, treadmill test, 2D echo and all those are done, and finally to have absolute surety, doctor asks you to go for troponin test. Troponin is a protein that is there in our blood, and that is basically troponin test is measured. So, suppose this we are measuring and its absorption is at 450 nanometer, the substrate absorption happens, and then at 450 suppose your absorption value is coming at 0.350 arbitrary unit. So, calculated troponin 1 level can be 0.045 nanogram per ml, that will diagnose myocardial infarction. So, if this value is coming, that is a biomarker. Now, that is a real world scenario, but suppose error is happening, your lambda max is 450.5. So, that is error is happening, and the spectral bandwidth is 2 nanometer, which is again a problematic, and a stray light is coming. So, that means your absorption that is measured, instead of 3.350, it is measuring 0.335, that means 4.3% lower than whatever it should come. And then you calculate the troponin C, it gives you value of 0.043 nanogram per ml. So, actually it should be this, but because of all these instrumental error that is happening, you are getting this, although it looks small difference, but you see here only with 0.02 nanogram per ml you missed the MI diagnosis, and that is a big mess up, right, that one can do with a human life. Therefore, the absolute calibrated instrument is necessary for when we are doing the biomarker discovery, right. So, therefore, the USP has set the standards, or ICH has set the standard, regulatory standards. So, wavelength accuracy should be 0.5 in this range of 300 to 1000 nanometer. Wrong lambda, wrong epsilon, that wrong absorptivity, wrong concentration, and that can be determinantal. Similarly, spectral bandwidth should be less than 2 nanometer for most of the application. That will lead to, if it is not there, lead to peak distortion and lambda max shift. The stray light should be 0.05 and then the absorption becomes unreliable if the absorption is more than 2.5. Then photometric accuracy, the detector that you have should be also very accurate, 0.01 to 0.02 accuracy. If it is not there, then quality control batch acceptance fails. And the linearity of absorption, right, you have to measure at different concentration and have a linear curve like this. If it is not 0.999, then a standard curve is unreliable, right. So, that is what one can learn it, the spectral bandwidth, the identity wavelength calibration, the quantify the stray light and minimize its impact, and then practical consideration of instrument and troubleshooting, you can do it, right. So, spectral bandwidth, how you do it. So, typically how it is done. So, let me give you a practical. When somebody sells you spectrophotometer, they sends an engineer for calibrating it, right. And the engineer does this three things that I mentioned to you: IQ, OQ and PQ. Installation qualification, operational qualification and performance qualification, right. But engineers does it and you believe that they are doing fine, but some of you may be engineer, right. So, you need to know what actually has to be done and how you calibrate it. So, essentially calibration means like you are calibrating very accurately what is the lambda max where it should come, what should be a spectral bandwidth and all those. So, how you determine that spectral bandwidth? It is a range of wavelength that passes through monochromator and reach to the sample, right, at any given nominal condition, nominal wavelength. So, passes, it has to reach to the sample, that is what spectral bandwidth means. And then measurement of spectral bandwidth, how do you measure this? Full width at half maxima, ऐसा curve है, this curve, where is the 50% that is coming? Full width at half maxima, full width at half maxima, this is the maximum. Half of that, how much the bandwidth, that is you measure full width at half maxima. So, how do you measure it? SBW, you have a slit width of where the light is passing, slit width. Then you have a focal length ratio of the lenses that you have and grating ruling density. These parameters come from manufacturer, and then you do the calculation, this KZ Rennie Turner monochromator calculation. So, slit width 0.2 nanometer, the focal length say 250 millimeter, the grating 1200 lines per millimeter, and then you calculate the SBW, which comes to be 0.67 nanometer. Now, measurement of bandwidth you can do using deuterium lamp, that is the standard protocol that is used by engineers. So, what you do? Place that deuterium lamp in a sample position and then set the monochromator at the H alpha line of deuterium, that is 656.1 nanometer. Then scan plus minus 10 nanometer around the peak, right. You are scanning from here to here, right, here. And then you take the full wavelength at 50% of peak height, FWHM here, and that is the SW lambda right minus lambda left, right. So, basic educational institute, what we have SWH, we measure it, take it to 5 nanometer. It can be done with a manual slit, and then this can be used like our MSc practical lab, we use this, teaching labs or routine screening. Resolution here is poor, but when we go to research grade, we need to have the spectral bandwidth of 1 to 2 nanometer. It can be done by the slit can be moved by motorized machine that we have. It is used for protein quantitation, the kinetics, its resolution is good. If you do more high precise, it is used in pharma industry, your spectral bandwidth is 0.5 to 1 nanometer and then motorized variable, and you can do even for trace analysis or peak separation, that gives you excellent resolution. And finally, UV NIR you can do it 0.1 to 4 nanometer, it is again motorized and automated, and you can do far UV structure, the full spectrum, and that is again excellent resolution. So, when we do SW measurement, if it is less than 1.5 nanometer, you say it is a pass, equipment is validated. If it is 1.5 to 2.5 nanometer, it is acceptable for most of the cases, but if it is like a between 2.5 to 4 nanometer, you have to be really cautious, because now we are at the edge. So, you should have to call someone, and if you reach this more than 4 nanometer, its instrument requires service or repair. Now, you understand that why a spectrophotometer, some can be very cheap and some can be very expensive, like relatively expensive. It depends upon how precisely you are measuring all these or obtaining all these parameters. So, your spectrophotometer you can get in 2 to 5 lakhs as well, and 40 to 50 lakhs as well, depend upon how precision accuracy you are obtaining. So, when somebody says the spectrophotometer you can get in 2 to 5 lakhs, you know that some parameters are not that precise, right. So, for some application you require high precision, some application you do not need. So, you do not need to spend that much money, right. So, how spectral bandwidth distorts in UV vision measurement. So, let us say it can come, the distortion can come from various factors. So, let us consider a narrow spectral bandwidth, sharp well defined peaks we have, find spectral visible line we have, and then lambda max is very accurate. But in broad case, the flattened peak you have, it is not very sharp, but rather flattened, and lambda max can shift here, right. So, if a spectral bandwidth is 0.5, you measure the lambda max 280, and then lambda max error is 0, and here is the 0, accurate measurement happens at 280. But suppose we go to 4 nanometer, our lambda max goes to 280.5, you have a error in the lambda max, and that basically leads to 18% like 0.18% error, and that leads to change in the extinction coefficient by about like a 0.18 or 0.2. So, extinction coefficient sensitivity is very important, right, for like a troponin C, as I mentioned, it can change and give you the wrong value, that is what we said. So, effect 2 can be photometric accuracy and spectral bandwidth trade off, right. So, if you look at spectral density proportional to bandwidth square, right. So, if narrow bandwidth, weak signal, short noise dominates, high photometric error. If you are getting more flux, less relative noise, low parameter. So, one has to trade off between the sharp spectral width and photometric accuracy, right. So, you have to balance between these two, whether we are sending enough light to the detector for using it. So, effect of spectral bandwidth on protein quantification, I said if the spectral bandwidth is not very accurate, we get wrong quantification. Let us look at the pure protein versus contaminated sample, like a contamination can come from DNA. So, you remember we do this DNA quantification 260 by 280 ratio, 260 DNA, 280 protein, right. So, say pure protein, true 260 by 280 is coming 0.575, and protein plus DNA 1.2, and high DNA content 1.8. So, measure at 1 nanometer of bandwidth, these values are here, right. So, here true, and this is measured with 1, and if you are measuring with 4 nanometer of bandwidth, you see some error has been introduced about 1 to 1.5%. So, narrow bandwidth is something like 260 and 280, broad bandwidth you get at that is what. But broad bandwidth, there is a as I was saying in the previous slide, this intensity is more because more light is reaching to detector, the accuracy can be slightly compromised, right. So, wavelength one has to really calibrate it, and as I mentioned we can calibrate using deuterium lamp and so. And now, in this case wavelength accuracy and calibration is extremely important, but if it is not calibrated you introduce error. So, let us take an example of IgG quantification, that IgG immunoglobulin quantification, you know this is used in many of the antibody based detection. So, wavelength selected we have 280, wavelength actual is suppose it is changing. So, error is also getting introduced. So, 280, 280.2, 280.5, 281 error is introduced and therefore, quantitation is introduced. So, clinical relevance, like again you can miss the diagnostics of when we are detecting it. So, now you understand why this accuracy is very important, right. So, wavelength accuracy and calibration, you can have a mechanical drift, thermal effect, optical aberration and detector misalignment and all those points that can introduce various kind of error, and one can correct it. Like a mechanical calibration, you can do a single point calibration. Thermal effect, you can stabilize, you can have a thermal stabilizer, temperature can be stabilized. Then optical aberration, like a whole helium oxide multi-point calibration one can do. The detector alignment, you have to call engineer and get it serviced, and then you have to do periodically calibration. So, therefore, what I mean to say in a simple term, that these instruments should be calibrated and authenticated on a periodic basis if you are doing the quantitative assessment of say biomarker or anything, and these are the way you can do the calibration, right, by deuterium lamp, H alpha, H beta, H gamma and mercury lamp. You have in visible range, green range, blue range and the UV visible range, and you can have for like a sharp stable secondary and alternative reference for these. And using this basically you can calculate or calibrate the standards, right. So, how frequently you should do this, right. So, implementing and maintaining the wavelength calibration, how frequently one should really engage into. So, daily routine QC you can do weekly, right, you check it. Reason it can happen because of mechanical or thermal drift. It is given how to calibrate it in this USP, US Pharmacopoeia guidelines. When we are working with this instrument in pharmaceutical setup, like a pharmaceutical manufacturing, how frequently we should do? After every 50 to 100 samples one should do, and this comes GLP compliance. GLP is good laboratory practice compliance, right, one has to do, and this is given in FDA or ICH-Q2 guidelines. So, when we are using this instrument in manufacturing setup, the calibration should be done in this region. If you measure 100 samples, you should go and do it. When we are doing for research and kinetics, monthly you should do it. The wavelength accuracy 0.1 should be there, and this is a good laboratory practice that you need to do. And after service and repair, immediately you should get it done, realignment should be done, and that is a manufacturer requirement one has to do. Temperature change, if something is changing, right, more than 5 degree, when your AC is going off, thermal drift can be there, and then you should the standard practice for calibrating it. Extended wavelength range, if we are doing it like a very far wavelength range for some measurement, then you use this every quarter you should put it, like when UV or NIR drift you can do. So, extended range recommendation should be first of all there, and then you can quarterly engage this, and then helium oxide check quarterly one should do it. That is a best practice for doing it, right. So, wavelength calibration data you can put it, deuterium line, measure the value, reference, how much error and what is the error, and one can do linear regression for doing this calculation, and finally your engineers calibrate the instrument to get it, right. So, that is what essentially is required, wavelength calibration and validation frequently to get the instrument in order. Another one was stray light. So, most serious measurement limitation that happens. Now, stray light, light that is to detector from the wavelength can be also checked. If it is less than 0.05, it is excellent. It is a research grade measurement happening, trace analysis kinetics one can do. If it between 0.5 to 1, it is a good standard laboratory work one can do. If it is 0.1 to 0.05 acceptable, routine analysis one can do, clinical diagnostic analysis, and if it comes in poor and unacceptable range, you should not rely on this. So, essentially you have to get it done, right. So, stray light can come from anywhere, it can come from like a grating interference, can come higher order diffraction, it is optics based experiment, one can come from here, optical reflection, aperture leakage, fluorescence, sample induced event can come, dust or fluorescence coming from sample can lead to error. So, this has to be taken care in the calibration and making of the instruments, right. So, at same when this stray light is coming, you can minimize it, put it in the dark, and grating can also help in calibrating it. So, basically it is all optics, the dichroic mirror, the interference filter, that basically can help in order sorting filters, can help in removing all those stray lights that comes, right. So, so these are some of the error that can come. I will leave these slides for you to read it, and basically stray light testing and measure acceptance one can do, the background absorption test, simple test one can do, and also photometric linearity test you can do, like use the calibrated neutral density filters for measuring the how much stray light is coming, and get the stray light limit that is there during the calibration of the instrument, right. So, this is the true spectrum. If the stray light is free and measure with a stray light, you can see lambda max is shifting, such case should not be there. So, it can distort the protein quantification and kinetics, and therefore, instrument calibration and stray light measurement is extremely important, right. So, now so I would say there are like all the guidelines there of filters, what range should be used, how we do the photometric accuracy measurement, and that one can take it in consideration during installation qualification, operational qualification, what you do, and then performance qualification. So, performance qualification one has to do wavelength calculation, stray light, linearity, and then the lamp validation on various samples that you use it. So, I leave upon you to go in details of these information that I am sharing with you, and finally, actually some of the common problem that I am going to tell you what people can face it. So, common problem and diagnostic approach, one can have a baseline increasing without sample, slowly increases during the scan, right, that is the symptoms, and it can cause the air bubble in the cuvette. Many times it is not instrument, it is your sample, right. You can just do like this, visualize, inspect it and refill the cuvettes, purge the bubble, and then you can have a better spectrum. You can have a blue light shift between the scans. So, temperature is not stable, you have to monitor the room temperature, put your room temperature in a stable condition. So, wait for 30 minutes, warm up and thermostatic jacket, and then reuse it if temperature is not stable. It can be random baseline spikes. So, electronic noise is getting introduced, check the electrical connection, and then shield the cable and check the grounding. These are very important one. For getting the noisy data, that can lead to high standard deviation, right. So, like suppose your CV is more than 5% of variance is more than 5%, it can come from insufficient signal, right, narrow, you have set too narrow spectral bandwidth. So, reduce the spectral bandwidth to measure A and widen it to use for then you have to increase it, have a longer path cell. You can have a sporadic spike in the spectrum, it can be because of dust particle, your sample is not clean, and check the sample, right. So, clean it, filter the sample, then reuse it. Random noise can come, so then PMT detector is aging, it is not able to detect it correctly, just replace it, right, and replace the PMT tube. So, these are some of the error. Then you can have an unrealistic peak shape, right. If it is coming, either it can be because of spectral width is too high, stray lights is coming and all those. So, you have to again calibrate it. If high absorbance is coming, that is not reliable, right, it becomes unreliable. So, measure the absorbance, decrease the sample, and then like do the dilute the sample less than 2, right. One I can do with a KSCN test to find it out. The non-linear response is coming, again photometric calibration is needed. If the concentration appears low, the sample precipitates. You can filter the sample, check the pH, ionic strength and redo the experiment. So, these are some of the troubleshooting that one can do of the artifacts that are coming, right. So, selection of optimal setting and application. So, wavelength one has to do, bandwidth we have to select, the range where we can have a linear effect, and path length how much we should have, then validation is extremely important, and frequency how frequently we should measure. So, these are some of the parameters for protein concentration that has to be taken care. If we are doing the kinetic measurement like enzyme kinetics, your wavelength has to be chosen, because most of the dye that PNPP dye we use, and that is a maximum sensitivity. Spectral bandwidth we have to choose it correctly, that we get the fine time resolution. The target range, absorption range you have to choose, the path length you have to correctly put it, and sampling time how frequently we sample, what should be temperature control, because we are looking at the kinetics, right. So, this rate can depend upon the temperature. So, one has to have a precise temperature done, and calibration immediate before assay and then wavelength is stable. So, these are the some of the tips that one can have while doing the experiment. Now, when we are doing the thermal denaturation like protein stability and TM, you again choose the wavelength correctly, spectral bandwidth correctly, target range correctly, temperature range how much we are heating it up, right. So, let it slowly happen, then the data point interval how frequently we should have 0.5, then path length 1 centimeter, baseline correction one has to do. When we are doing for ELISA or high throughput 96 well or 384 well plot, then we are measuring some of these like dyes or in visible range. ELISA standard readout, so 450 nanometer. The spectral bandwidth should be 2 nanometer. Then reference wavelength 630 should be there, and path length, because it is in 96 well plate 0.05, and then well spacing should be like a follow the plate layout automatically, calibration one has to do, and you have to put the plate in proper orientation, that is what one can do it. You can have like a you when we are using for pharma application, you have to meet the USP, ICH or FDA standards. So, they have given the parameters, one has to match it very carefully, like a photometric accuracy you have to match, wavelength accuracy you have to match, standard bandwidth you have to match, and then linearity should be there, precision should be there. So, all these parameters has to be extremely carefully calibrated, and that can be then it can be used in a pharma application. So, yes, so this was exposure for you to how we can use this UV visible absorption spectroscopy in pharma, and some of those that I have taken basically are given here. So, if you are interested to deep dive into this concept, you can go through these documents and let me know if you have a question during the question session. So, thank you very much, and next class we will start with the next topic. Thank you, looking forward to having the next class. Thank you.